You know, a lot of people think AI is basically magic, right? Well, today we're going to pull back that curtain. We're going to see that teaching a machine to think isn't some strange dark art. It's actually a really fascinating engineering process. So, think of this as the builder's guide. Let's jump in.
Okay, so let's get right to it with the big question. Imagine you're the one in charge. You have to teach a computer to play a game, like checkers, completely from scratch. Where would you even start? And this isn't just some abstract idea, right? This is the fundamental design challenge we're going to tackle together. This is our builder's journey.
So, here's the game plan. First, we're going to talk about the why, the dream of learning. Then, we'll lay out our blueprint by defining the game. The main event, of course, is actually building our checkers master, step by step. And finally, we'll zoom out, look at the bigger picture, and see what's on the horizon. All right, let's do this.
Okay, so first up, why even bother with all this? What's the point of teaching machines to learn, anyway? What's the big dream here?
So why is this stuff so important? Well, it's a total game changer for problems where you just can't write down a simple list of rules. I mean, think about something like face recognition. You could never program a computer by hand to recognize every possible face. Instead, you give it tons of examples and let it figure out the patterns. It's how we build systems that can tackle insane complexity, adapt on the fly, and personalize our entire world.
Okay, so before you can write a single line of code, you need a blueprint, a solid plan. In the world of machine learning, this is called creating a well-posed learning problem. And honestly, it's the most critical step. All right, pay attention here, because this is like the golden rule for everything we're about to do. A machine learns if its performance, let's call that P, at some task, we'll call that T, gets better with experience, which is E. Just remember those three letters, T, P, E. Task, performance, experience. This simple framework is the absolute first thing you have to lock down for any ML project. And seriously, I can't say this enough. Nailing down your task, your performance metric, and your experience with total clarity, that's everything. It's the difference between a project that actually works and one that just goes nowhere. It forces you to define exactly what you're trying to build. And this is where it all clicks into place. Look at how this TPE framework works in the real world. For our checkers program, the task is playing checkers. The performance metric is simple. What percentage of games do we win? And the experience, playing thousands of games against itself. But look at the robot driver. Same framework, totally different problem. The task is driving, performance is how far it goes before messing up, and experience is watching a human drive. It's a universal blueprint.
Okay, we've got our blueprint. Time to get our hands dirty. We're going to walk through the 4 huge design choices you'd have to make to actually build this checkers program. This is where the real building begins.
So, building this thing really comes down to making 4 big decisions. First, what's the training experience going to be? How does it practice? Second, what's the target function? I mean, what are we actually trying to teach it? Third, how will it represent that knowledge? And finally, the learning algorithm. How does it actually get smarter?
So, decision number 1. What kind of teacher are we going to give our program? We could use direct feedback, where for every single board, an expert tells it the perfect move. Super easy to learn that way, right? But what's more realistic is indirect feedback. It just plays a whole game and at the very end it's told you won or you lost. Now it has to figure out which of its moves were brilliant and which were blunders. That's a classic problem called credit assignment, and it's way, way harder to solve.
And that brings up a huge problem, right? How does a machine even know what a good move is? Good is a human idea. We have to translate that into something a computer can actually work with, something it can measure and optimize. We have to give it a concrete target.
And here is where we get clever. Instead of trying to teach it this really complex thing, how to pick the best move, we're going to teach it something way simpler, just how to score a board. We create this target function, let's call it V of B, that looks at any board B and just spits out a number. A high score means the board is great. A low score means it's terrible. A win might be plus 100, a loss minus 100. Now its strategy is easy. Always make the move that leads to the board with the highest score.
But okay, how do you even store a scoring function? You can't just have a giant list of every possible board. That's impossible. So instead, we represent it with this, a linear function. And I know, you see an equation and it might look a little intimidating, but don't worry. The idea is actually super simple. It's just a way of adding up the values of different features on the board. The real secret sauce is in those W's, the weights. Those are the numbers the machine has to learn.
So what are these X's in the formula? They're not scary. They're just things we can count on the board. Like x1 is just the number of black pieces. x2 is the number of red pieces.
x3 is the number of black kings. Simple, right? The whole learning process is about the machine automatically figuring out the importance of each of these features, which is its weight. For example, it needs to learn that having more kings is way more important than just having more regular pieces.
Which brings us to the million-dollar question, right? We've got our features, we've got these weights, but how does the machine actually learn what the right weights are? How does the thinking actually happen?
This formula, this is the engine. This is the heart of our learning machine. It's called the LMS, or Least Mean Squares Update Rule. Yeah, it looks a little crazy, but trust me, what it's doing is actually beautiful and simple. Let's just talk about what it does.
So let's break that down. Forget the symbols for a second. Here's what's happening. After a move, the system compares the score it predicted with what actually happened. If its prediction for a board was too low, the rule just gently nudges up the weights for the features on that board. If the prediction was too high, it nudges them down. That's it. It's this tiny, constant correction over and over and over again. You do that thousands of times over thousands of games, and those weights slowly get more and more accurate. The machine learns.
And boom, here it is, the whole system working together. You've got the performance system, that's the part that actually plays the game. The critic looks at what happened and creates a training example. The generalizer, using our LMS rule, takes that example and tweaks the weights. And the experiment generator just says, okay, cool, let's play another game. It's a complete self-improving loop.
So there you have it. We built a checkers master. But, and this is super important, this is just one way to do it. The design choices we made are just one path. Let's zoom out for a second and appreciate the bigger universe of possibilities.
For instance, sometimes you don't care about a score. You just want a simple yes or no. Like, is today a good day for water sports? That's a totally different kind of problem. It's called concept learning, where you're trying to learn a simple yes/no rule from examples. It uses a whole different toolkit than our checkers player.
And all this leads us to what's next, because this stuff is far from a solved problem. I mean, this is one of the hottest, most active areas of research in all of computer science right now.
People are tackling these massive, fascinating questions every day. Like, how do you know when you've trained it enough? Is there a way for the system to be curious, to seek out the most interesting new games to play to learn faster? And maybe the holy grail of it all, could a system ever learn to invent its own features, to automatically change its own representation of the world? These are the questions that are driving the future.
So we've gone on this whole journey, right? From a simple question about a game to a full-on blueprint for a thinking machine. We've seen it's not magic, it's just a series of really smart, deliberate engineering choices. Which leaves me with one final question for you. Now that you've seen the blueprint, what problem would you teach a machine to solve first?